Hey, hey, hey! Here we are with our 2.3 notes, which is row operations. So our essential question is, how do we use row operations to get a matrix in row echelon form? So that is row echelon. That's how we pronounce that. So before we begin, there's a couple of things that we need to know. One of them being, what is a matrix? What does that look like? How do we put that into the calculator, etc., etc.? So a matrix is just an array of numbers. And the way that we formulate a matrix is that we use little square brackets, and then we're going to array or arrange some numbers in rows and columns. So we know that rows are going horizontally and columns are going vertically, right? So when we talk about a matrix, we need to know the dimensions of that matrix. And the dimensions of a matrix are always listed rows by columns. When you put a matrix into the calculator, it's going to ask for the dimensions and it uses M by N. Do not ask me why they don't use R and C for rows and columns because I don't know the answer to that. But M by or times N is going to be the dimensions, and it's always rows by columns. So here's where we're starting in our notes. It says find an augmented matrix for the system. So what that means is that we're going to use this system in example A, and we're going to write a matrix for it, specifically for it. And the way that we do that is we use the coefficients of every variable along with the constant. So equaling that number, that is your constant here. When it's equaling some number, that's what an augmented matrix is. So in this particular example, we have 1, 2, 3 rows, and we would have one column for the X, one column for the Y, one column for the Z, and then one column for the constant. So this would be a 3 by 4 matrix. This is rows, this is columns. Okay, you need to know the difference. So I'm starting with my bracket. I need to make sure that it's in order of X, then Y, then Z, then equaling a number. And all I'm going to do is put the coefficient of each variable and then the constant. So in this first equation, I have a coefficient of 1, -2, 3, and then a constant of 9. So that is my first row. My second row, the X has a coefficient of -1. The Y has a coefficient of 3. There is no Z variable, which means I need to put a 0 in its place because really 0 times anything is 0. So if you don't have a variable in the equation, you need to put 0 as a placeholder. And then what is the constant? -4. So there's my second row. My third row would be 2, -5, 5, 17. And here is my 3 by 4 matrix, and this is the augmented matrix for that system. Sometimes in augmented matrices, you will see either a dash line between the coefficients and the constant, or sometimes you see a solid line between those coefficients and that constant. It doesn't matter if you use the solid or the dashed. Sometimes you don't see it at all. Sometimes you only see it maybe like a colon right here. It just depends on the program or, the who you are. You kind of have some options. So that is the augmented matrix for this first system. This would be a great time where you could pause and try the second one on your own. So in this second one, we have 3 rows. And we're going to have 4 columns because we do have 3 variables plus that constant, okay? So, I'll leave that to 3 by 4 matrix. So I want to make sure I'm going in order of X, Y, Z constant. So the first row would be the coefficient of X, the coefficient of Y, the coefficient of Z. I don't have it, so I put a 0. and then the constant is 5. Second row, coefficient of x, it's not there, 0 in its spot. Coefficient of y, coefficient of z, constant. Third row, coefficient of x, coefficient of y, coefficient of z, constant. And there's my augmented matrix. Okay. Sometimes I'll use the solid line, sometimes I'll use the dashed line, it just depends. So whenever I give you a system and tell you to write the augmented matrix, you need to figure out how many rows, how many columns, and you need to make sure it's going in order, X, Y, Z, constant. Okay, whenever you're putting a matrix in the calculator, it's gonna ask for the dimensions. Remember, it's R by C, M by N, rows and columns, okay? So then we get into this row echelon. That is a process that the calculator can do and that we can do by hand in solving a system. Remember, matrices was another way of solving a system. We learned how to graph, substitution, elimination. Now we're going to learn about matrices. So we can do it by hand, and we can also put in the calculator and let it do the work for us. So in example 2, it says use a graphing calculator to find reduced row echelon form for the augmented matrix to solve the system. So here's where I would like for you to pause and watch the video that I posted about using the Casio calculator to input a matrix and how to get to that reduced row echelon form. What you see in this purple box right here that's highlighted is how to get reduced row echelon form. So if you have that Casio calculator, you're gonna press your option key. Then across the bottom, above F1, F2, F3, F4, F5, above F2, you're gonna see MAT, which stands for matrix or matrices. So because that's what we're dealing with, you're gonna choose matrices, so F2. Then you'll see some more options, but what we want is not there, so we're gonna arrow over, which is option F6, to get more options. And then we'll finally see that RREF, which stands for reduced row echelon form. And that's what we want, because reduced row echelon form is going to solve the system for us. So what that's going to look like is that if we're solving a system and it's in terms of X, then Y, then Z, that are constant in the matrix, we're going to get something that looks like 1, 0, 0, a number, 0, 1, 0, a number, 0, 0, 1, a number. Because that literally means that X is equal to something, Y is equal to something, and then Z is equal to something. So this is going to be the format that we get once we put our matrix in reduced row echelon form, which the calculator is doing for us. Before you press these buttons to get RREF, you have to input your matrix into the calculator. And so the video walks you through on how to do that. If you don't have a Casio calculator at home, you can use the emulator for the Casio calculator that I have posted in the course information folder. And if you're still not comfortable with that, I also posted a link for the Desmos calculator with matrices. It's pretty self-explanatory. When you click on that link, you'll see in the bottom left corner, it'll tell you what are the dimensions of your matrix. And so you'll put in like 3 by 4, or maybe it's a 2 by 3 or whatever. And you'll physically type in all the numbers. And when you hit enter, you will have some options, and one of them will be RREF. And so you'll choose RREF, you'll type in the matrix name, which will most likely be a capital A, and then it will solve the matrix for you. Okay, like I said, it's pretty self-explanatory if you're looking at that Desmos link, and if you're using a Casio, either one that you have at home or you're using the emulator, watch that video I posted. It's only like 3 or 4 minutes, and it's super explanatory, so it should help you. Okay. What I'm going to do here, though, is that we want to put our system into an augmented matrix first, because that's what we're going to input into our calculator. So here in example A, I know that I have 3 rows and I'm going to have 4 columns because I see 3 variables. So this is going to turn into 1, -3, 0, and 4, 1, 0, 1, 12, and then 1, -1, -1, 1. Okay, so this is what I'm going to be putting into my calculator. And once it's stored in my calculator, then I will go through these options here. I will go to option, F2, F6, F5. That will put RREF on my calculator. Then I'll type in whatever matrix it's in. Maybe it's matrix A or matrix B or whatever. And then when I press enter, it will give me something that looks like this. And that will tell me what each variable is equal to. Okay. When you do that on your calculator, your RREF will look like 1007 0101 and 0015, which means x equals 7, y equals 1, and z equals 5. The first time you plug in matrices into your calculator, you're thinking, oh my God, this is hard. There's a lot of steps. But once you get used to it, your muscle memory takes over. You can solve a matrix like that. Super quick, super easy if you know these steps. Okay? So let's try it again. But notice in B, it's not in the standard form that we normally see. It's not x, y, z equals a number for all of the equations. So you want to make sure that you're rewriting that so it's in the order of x, y, z equals a constant. The first equation is good to go. The second equation needs to be rewritten. So all I need to do is add my 3y to the left. I don't have an x, but I have a positive 3y plus 2z equals 4. And then the last one, I need to subtract the 5y and subtract the z. So that's going to be 2x minus 5y minus z equals 0. Okay. So now that I have it all in the right format, I can then create my augmented matrix. So my augmented matrix would be in the first row, 1, -6, 0, 5. Second row would be 0, 3, 2, 4. And the third row would be 2, -5, -1, and 0. And so I can put this in my calculator, go through the steps of finding RREF, reduced row echelon form, and my calculator is going to spit out 1, 0, 0, -11/17, 0, 1, 0, -16/17, and 0, 0, 1, 58/17. I'm hoping that at this moment you're thinking to yourself, thank God I can put that into the calculator, because this means that x equals -11/17, y equals -16/17, and z equals 58/17. And if we had to solve that by hand, we would have most likely made some careless mistakes. It would have been a headache. We're working with these nasty fractions. It would have been a mess. So we are very, very happy that we now know how to input our matrix into the calculator and tell the calculator to put it in that reduced row echelon form for us, because that's immediately giving us the answers. Okay, so like I said, I know the steps in the calculator may seem weird at first, but once you go through it a couple times, I promise it's going to become muscle memory. It's going to be so much quicker and easier to solve these matrices and these systems using the matrices in the reduced row echelon form. So I said earlier, we can use matrices in the calculator, but we can also solve them by hand, okay? And to do that, we're going to use the row operation. So in this highlighted box, I'm giving you the elementary row operation. So these are the three things that we can do all the time to rows in the matrix. So one thing we can do is we can interchange two rows. So if I want to swap row 1 and 3 or row 2 and 1, I can do that. And you may be thinking, well, why would that be beneficial? Well, maybe you have something like 001 number in your first row and something like 100 number in your last row. Well, you'd want to switch those things around because then that means X is equal to that number and then Z is equal to that number. You want it to look like I have up here. This is what we want it to look like, where those ones are along the diagonal, X, Y, and Z, and then numbers in that last column, okay? So we can interchange two rows. That's easy enough. We can multiply a row by a constant. Think about when we solve systems by elimination. Sometimes we have to multiply an entire equation by a number, whether it's a negative or a positive or whatever. So that's the same thing. We can also add a multiple of a row to another row. So I could multiply one row by a number and add it to another row to replace that row. I know this sounds a little confusing, but it's not that bad, okay? Now we have two processes. One of them is Gaussian elimination. So Gaussian elimination, it says we use row operations to get a matrix in row echelon form, not reduced row echelon form, but just row echelon form. So take a second there and then look at the difference of this one down here, which is Gaussian-Jordan, or sometimes we just call it Gauss-Jordan for short. And it says we're using those row operations to get a matrix in reduced row echelon form. So that's what we were talking about earlier. Ones along the diagonal, numbers in that last column. That's reduced row echelon form. Row echelon form has the numbers along the diagonal, but we could have some ones along the diagonal, but we could have some numbers above that diagonal. Still have our column of numbers at the end. So zeros everywhere, ones along the diagonal, zeros underneath it, but numbers can be above it. I know you're probably thinking, what the heck are you talking about, lady? Just stick with me. We'll be all right. Okay, so first thing I want to do is I want to write my system as an augmented matrix. This is going to be a 2 by 3 matrix because there are 2 rows and 3 columns. So this matrix is going to be 1, 1, 1, and then -1, 1, and 1. So our goal is to get ones along the diagonal and 0 underneath it. Well, lucky for us, we already have ones along the diagonal. All we need to fix is that -1, and we need to turn it into a 0. So what can we do? Well, I don't want to interchange my rows because I don't need the -1 up top. I need it to stay where it is so I can just turn it into a 0. Do I need to multiply a row by a constant? Not really, because then that's going to change my diagonal of ones, and I don't want to do that. But what if I add a multiple of a row to another row, or just add a row to another row? What happens when I add rows 1 and 2 together? Well, 1 plus -1 is 0. So maybe I want to add row 1 to this row to replace it. If I do that, my first row will stay the same. When I add these 2 rows together, so 1 and -1 is 0. 1 plus 1 is 2, and 1 plus 1 is 2. Well, you're thinking to yourself, well, Miss Treese, you got rid of your 1 on the diagonal. That's okay, because now I have my 0. And what I can do now is I can multiply this second row. I can multiply by 1/2. I can multiply a row by a constant. 1/2 is a number, that's fine. And when I do that, I don't mess up my top row. I don't mess up my 0 because 0 times anything is 0. And I get my 1 back, and then this also turns into a 1. I have ones along my diagonal and I have a 0 underneath the diagonal. This is row echelon form. So what does this mean? Well, this means that my y is equal to 1. That's what that bottom row means. Well, if I know that y is equal to 1, I now know my top row is representing x plus y equals 1, but y is 1. So that means x is 0. Sometimes it's easier to think of this as just a normal system that you're solving by substitution or elimination, because it's really the same idea, okay? And you might be thinking, well, then why don't we just do that? We just have, it's one of our teaks. It's one of the things that we need to learn how to do, okay? So it wasn't too terrible. It's kind of like with the calculator. The more you do it, the better you are, okay? So let's try it again. Here in part B, we have another 2 by 3, okay? We have 2 rows, 3 columns. So when I write my augmented matrix, that is going to be a -1, -1, 6, 7, -3, and 18. So here's my augmented matrix. So now I'm going to do some row operations to get 1s along the diagonal and 0s underneath. So the first thing that I'm seeing is I want to try to get the 0 in the bottom left corner. Typically, once you get the 0s where you want it, everything else will be pretty easy. So try to get the 0s first and then get your 1s along the diagonal. That's a helpful tip, okay? So get your 0s first and then get the 1s along the diagonal. So to get the 0 in the bottom left corner, what I can do is I could say, well, I could multiply row 1 by 7, and then I could add that to the row 2, and that had the -7 and the 7 canceling out to give me 0. So I'm going to add a multiple of a row. So I'm going to add 7 times row 1 to that second row. And that's going to get me nothing different in row 1. But if I multiplied row 1, I would get, by 7, I would get -7, -7, and 42. So if I add that to the second row, I get 0, because -7 plus 7 is 0. Then I get a -10, because -7 plus -3 is -10. And then I get 60, because 42 plus 18 is 60. Okay? So now I need to try to fix my -1, turn it into a +1, and I need to fix that -10 and turn it into a +1 as well. So I'm going to focus on my -10 first. And what I'm going to do is I'm going to say, well, I'll just multiply this by a -1/10, because I need to turn into a +1. So that becomes -1, -1, 6. That doesn't change. This is still 0, because 0 times anything is 0. This is now going to be a +1, and this is going to be a -6. Now all that's left is to turn that +1, that -1 on the top left corner into a +1. And all I need to do is multiply by -1. So if I multiply by -1, then that's going to be 1, 1, -6. Didn't change anything with my last row. I have 0s along the diagonal, and I have 1s along the diagonal, and I have a 0 underneath. So this tells me that y is equal to -6. And the first equation is x plus y equals -6, but y is -6. So that means x is 0. We have one more problem, and this time it's a 3 by 4. So we're adding another row, which essentially adds another column. What we're going to do is we're going to do Gaussian elimination to get it in row echelon form, and we'll solve. But then I'll also continue the process for Gaussian Jordan to get it in reduced row echelon form. Okay, so here we go. Hang with me. Last problem. First thing, I want to write my augmented matrix. Everything is in the right order. X, Y, Z equals constant. So I write my coefficients. 1, -2, 3, 9. -1, 3, 0, -4. 0, -5, -14, -23. Okay, remember, if the variable's not there, you have to put the 0 in its place. So remember, this time we're looking for ones along this diagonal, and we need everything underneath the diagonal to be a 0. Thankfully, we already have 1. We need to change that -1 into a 0, and we need to change the -5 into a 0. And we need to fix the 3 and the -14 on the diagonal and make them 1s. Well, I can immediately make that -1 a 0. And how can I do that? I can add, let me change the color. I can add row 1 because 1 plus -1 is 0. So that's going to get me to, I'll come over here, 1, -2, 3, 9. Nothing changes there. -1 plus 1 is 0. 3 plus -2 is 1. 0 plus 3 is 3. -4 plus 9 is 5. Nothing changes in the bottom row. Oops. So now I have 2 zeros underneath the diagonal. Life is good. Getting there, right? What I'm encouraging, like I said earlier, the helpful tip is get all your zeros first and then work on your 1s. So now my goal is to make that -5 a 0. Well, because I have a 1 right above it, I can easily multiply that second row by 5 and add it to row 3. And then that's going to replace that -5 with a 0, which is what I want. So I'm going to add 5 of row 2 to that last row. So again, nothing changes in the top 2 rows. Okay, so what you can do is maybe write out 5 times this second row would be 0, 5, 15, and 25. And so you're adding it to that bottom row. So 0 plus 0 is 0. -5 plus 5 is 0, which is what we wanted. -14 plus 15 is 1. Ooh, that worked out in our favor. And then 25 plus -23 is 2. I'm done. I have 1s along my diagonal and 0s underneath. Hallelujah, praise the Lord. So what does that mean? Well, that means that Z equals 2. Going up to the second row, that's representing Y plus 3Z equals 5, but Z is 2. So I substitute. So Y plus 6 equals 5, so Y is -1. So if I know Z is 2 and Y is -1, then I can substitute it into my first equation, which is really representing X minus 2Y plus 3Z equals 9. Don't know X. Y is -1. Z is 2. Simplify. Combining like terms and solving, X is 1. So I get X is 1, Y is -1, and Z is 2. That, where we ended in yellow, was using Gaussian elimination. So I got it to row echelon form. What if I want to use Gauss-Jordan and get it to reduced row echelon form? Well, then I would continue, because then I would want to get, let me change colors. Then I would want to get not only the 1s along the diagonal and the 0s below, but I would also want these 3 numbers to be 0. Remember? Diagonal of 1s, 0s everywhere else except for the last column. So let's continue to see if we could get there. So we're at this yellow matrix. And so what we could do is we notice, oh, I have the 3 and the 3 above each other. If one of them was negative, then I could combine them and get a 0. Smart move. So let's say we subtract 3 of row 2. So that would get us, wait, 3, yeah, no, minus, hold on. Oh, no. I take that back. You could do minus like negative row 1 and add it to row 2, but then you're gonna mess up your 0 right here. We don't wanna do that. So what we're gonna use is the 1 along the diagonal, that bottom 1. So we're going to actually subtract 3 times row 3. Remember, 0 times any number is still 0. So if I multiply my bottom row by 3 and then add it to row 2, or subtract it, you're multiplying by negative 3 and adding it. But so that's going to get me, come over here, nothing changes in my top row. Okay. My bottom row is the one that's being multiplied by the negative 3, and I'm combining it with the second row. So 0 times 0 is 3. Oh my God. That would be 0, 0, 3, and then 6, right? Negative 3, negative 6. So 0 plus 0 is 0. 0 plus 1 is 1. Negative 3 plus 3 is 0. Negative 6 plus 5 is negative 1. Nothing changed in the last row. We changed it to use it with something else, but we didn't change it to replace it. Okay, so now I still have my 1s along the diagonal. I still have all my 0s underneath, and now I have one of my 0s above. So now I'm just worried about that negative 2 and that 3. So now what I can do is I can multiply the second row by 2 and combine it with the first row to get rid of that negative 2. So I'm going to add 2 times row 2. And that's going to get me, well, the new second row would be 0, 2, 0, negative 2. So I'm combining that with the first row. So 0 plus 1 is still 1. 2 plus negative 2 is 0. 0 plus 3 is 3. Negative 2 plus 9 is 7. Nothing changes in the second row. Nothing changes in the third row. So I'm still looking good. Still have my diagonal of 1s. Still have 0s beneath it. I have 2 out of the 3 0s above. So now I just need to fix that 3. And so what I can do is I can use that row 3 again and multiply by negative 3 and add it to row 1. So I'm either adding a negative 3 or just subtracting 3 of row 3. So if I multiply this by 3, it would be 0, 0, or negative 3, sorry, negative 6. And if I add that to row 1, 0 plus 1 is 1. 0 plus 0 is 0. Negative 3 plus 3 is 0. Negative 6 plus 7 is 1. Nothing changes anywhere else. And hallelujah, praise the Lord, I have gotten it in reduced row echelon form. And this literally tells me that x equals 1, y equals negative 1, and z equals 2, which is the same exact thing we got up here. Okay, I know this seems long and drawn out. I know that it may be confusing. And really, there's so many different ways of solving, just like in algebraically with our systems, with substitution and elimination. There's so many different ways that you can approach these. Just know that you're not going to have a ton of these on the test, okay? We know that maybe the integrity wouldn't be there if we said do it by hand, because you could just punch it in the calculator and get the answer, okay? So it's just something in the TEKS that we need to teach you. And it's something that you should know how to do, but it's not going to be heavily tested, okay? So if it's giving you some anxiety, It's okay to kind of just brush it in the back of your brain, all right? One last thing before I let you go. Just like we talked about when we're solving algebraically a system, we could have infinite solutions or no solutions at all. Well, what is that going to look like if we punch it into the calculator and let the calculator do the work for us? It's not just going to pop up with words of no solution and infinite solutions. It's going to give you a matrix where you need to decipher what the numbers mean, okay? So, if you get a matrix with 3 zeros and a number, you should know that that's representing 0 equals a number, which is a false statement, which means no solution. If you get a row of all zeros, then that means 0 equals 0, which is a true statement, which means infinite solutions. Okay, so when you tell your calculator to do RREF, reduced row echelon form, you should be getting that diagonal of ones, and that's going to tell you x equals some number, y equals some number, z equals some number. If you get zeros and then a number, that's no solution. If you get all zeros, that means infinite solution. Okay? The calculator will show you a matrix that looks like this, and that'll be your key. Hope you stuck with me. Make sure you're watching that video of how to put the matrix into the calculator, and either that or using the Desmos matrix solver, so it's up to you. But let me know if you have any questions. Adios.